showing that there is such a gallery. Now we'll make the proof more aesthetic if we allow the gallery to be something like this. We allow trivial subspaces. Okay. And then what we want to prove is that, well, Alex just reminded us, but I'll say again that every gallery, every, what do we call them? Chambers, every two chambers, V and U are connected by a gallery. And so, you said what a gallery was, or you remember what a gallery is? Okay. Now, so we first define what the difference between two galleries is. So, two chambers is, excuse me. So we define, you can define functions vi, v, u, the dimension of intersection. And let's also define this to be the sum. And we also define the metric to be this. Okay. And now, basically, now that we have this sort of a discrete metric, so all we need to show is that we can do one step. We can take two different chambers and you can make the distance a little bit shorter. Okay? So what we want to prove is that if the distance between V and U is non-zero, then there are two chambers which are sort of neighbors of the original ones, i.e. their intersection is larger than n or equal to n. And the distance becomes small. Okay.
V prime and U prime are two chambers.
Two, yes.
And by intersection, you mean number of spaces which coincide with this chamber.
Right. Yeah. So this basically means that they're either exactly identical or that their intersection is a wall. Okay. So basically, we see that these functions, these di are increasing or non-decreasing, and they go.
Wait, what is it though? The VU is equal to what? The sum between
the sum of I from 0 to n minus 1, n plus 1, and n.
But sum of what?
Of I, sum of I. Sum from I.
You should take it in brackets.
Right.
I mine?
No.
No, this is.
Alex,
So to prove this, so sort of easy observation is that if the distance is larger than zero, then there is an I such that sequence has to be constant a little bit, and then it has to increase. And so we can pick some vector which is in the intersection here and not in the intersection here. So pick some W and Vi plus 2 intersection Vi plus 2 minus Vi UI. And then basically what we do is that we just, what we want to do is we add W in the I plus 1 dimension. Instead of, we replace Vi plus 1 with Vi and W. Okay, right there.
I don't understand something. What is V prime intersection V is greater than equal to what?
N.
What do you mean by that?
Did I get that wrong? N minus 1. No, N. Right? So we have, each one of them has N plus 1 members.
You think of it, you think of a flag as including also
Also the trivial,
the two trivials.
that's what you...
And there you meant capital G, right?
Okay.
There you meant capital G. Small gi is not defined.
You really mean that they are neighbors, right?
I don't see where you mean.
Here you
Yeah, it's all capital, right? I forgot.
Then W is what? Vector?
W is a vector, yeah. Okay. So again, what I'm doing is just, instead of, I replace Vi plus 1 with Vi plus 1 prime, which, right here. Vi plus 1 prime, which contains the I and this vector from the intersection of the higher space. Okay. And similarly, I was replace Wi plus 1 with W, with U there, right? Ui plus 1 with Ui plus 1 prime, which contains Ui and W. Okay. These are the new, and then, so then V prime is just, it's just, we have this V0, V1 up to V I plus 1 prime, and the rest of them remains unchanged, and U prime is the same. And this basically, what this gives us is that the intersections of Vi plus 1 prime and Ui plus 1 prime is a little bit is one larger than the intersection of Vi plus 1 and Ui plus 1. Okay, so this is basically the proof of that. Okay. And so that's it. The diameter. Like what the question Alex asked, what the diameter of the gallery would be, right? That is what.
But everyone understood this point. So maybe illustrate what you're really doing. Like take a simple example, like it's in the top or in the level.
Well, I guess you could say. Well, if you had say V0 to V, let's say V1 would be span some vector E1.
So W is a vector, right? Maybe give it a different name. It looks like a subspace.
W is a vector, right? I don't know what different name should I give it. Alpha, say.
What?
Want a different name? Alpha.
No, right. To stress this is a vector.
Okay. Well, again, you know that at a certain stage, you have two things whose intersection is, say, this. This is at stage I, and stage I plus 1, you know that the intersection didn't change. But in stage I plus 2, you know that it did. So what you do is you just take a vector from here and you put it here. You change the...
What is the prime? No, I don't understand. What is vi plus 1 prime?
Yeah. So I'm saying. So, okay. Maybe I'll do it slower. Okay.
No, slowly and carefully.
Okay. So.
I already saw the proof and I don't understand you now. So
Okay, I'm sorry. So, okay. So.
This would be even more difficult for the other.
Okay. So we said that there's an alpha which is in vi plus 2 intersection and ui plus 2 and not in this intersection. So we pick. So basically we know that what we know is this, right? Okay, this is what we know, and we just want to. So what I want to say now, this could be either a vector space of dimension I plus 1 or dimension I if alpha is contained in vi, right? And same here. So I just take and the intersection of these two, the dimension of these intersections is larger than the dimension of this intersection because alpha is also here, right? Okay. So then, what I'm saying is that we can pick vi plus 1 prime, vi plus 1 prime, subspaces of dimension I plus 1, such that they are basically here. And then, so what's not clear? Okay. And then, so we pick. So the chambers we pick are.
We change the flag only at one coordinate in some sense, and that really means that this is you're going to a neighboring chamber because if they agree in the rest of the flag, and the way you change it is such that now we see that there is a new intersection between them. The alpha is inside both of them, so the intersection is bigger than what we had before. Okay, so I consider this done. Any questions or problems? So about the size of the gallery that connects two such chambers. So the bound I can say, I think that it has to be between twice the difference between them and once the between them.
but I don't know. I didn't speak about it in terms of n. What is it? N is like the.
What are your
You said
estimates?
n.
What are your estimates?
The size of the gallery that connects U and V. Okay. So I don't know.
Should it just be the number of basis vectors in which they're different?
Excuse me?
Should it just be the number of basis vectors in which they're different? Just switch one each time?
So what, what's
Yeah.
only?
Wouldn't it just be the number of basis vectors at which the two galleries differ, or the two subspaces?
You mean what would this be? What the size would be?
No, then
Or what this would be?
yeah, the distance between them.
Yeah, right. So the distance between them is the number in which they. Right. Yeah, so. And so
DUV is, what is this, at most what?
twice this. So this sort of.
What is it, DUV is at most, what is it's in the middle?
The G is the side of the gallery. Which
Size is the gallery.
It means the number of chambers.
And at most two, what we call DUV,
this part sort of follows from this algorithm.
Right.
We add two chambers and go down by one.
No?
And the other side is sort of.
And what's the maximum of DUV?
So it's
Sum of i's.
sum of i's minus, well, it's not really sum of i's, because the intersection of two large spaces has to be something, sort of, right? I mean, I don't know. I checked it once and I forgot already. So now sum of i's minus. Well, we know that the dimension of vi.
Can't it happen that VI and UI do not intersect at all?
Okay, it depends how large, right?
If you look at UN minus 1 and VN minus 1, they have codimension 1, so they must intersect. It's something, so.
So you could sort of use this to find what the number is exactly.
You can, that would be, but it's a level of n squared, I guess, something like. You can bound it by some constant time n squared, huh?
Well, so what is the sum of
What?
The sum of i's is the order of the square root. Then you subtract some parts.
So. Okay. Very good. רוצה להגיד משהו? זה אחרת לך שלך או ש... מה? Okay, maybe there is no point that I will start. HANA is a completely different proof, so why don't you show it? It would be nice. There's no point that I start the material now.
Okay, I prove it by induction model. Starting at 3, and then a chamber come by W1 inside W2, when it is one dimensional, this is two dimensional, and we want to pass from this to this. So the gallery we construct is we start from here, then go to W2 intersection U2 inside W2. Then W2 intersection U2. inside U2. And then we go here.
Just a second, how do you know the W2,
They are of coordination 1, the mass intercept.
the W2 and U2, maybe they're equal?
If they are equal, then this in itself is a gallery.
Then what?
Then this is a gallery if they are equal.
Just these two chambers together already go.
This is all.
Two chambers in
Okay, and then
one.
we finish. Okay, okay,
Yes.
so, okay, you said it. Okay. Either they are already.
Yes.
Fine.
So we get that for n equal 3. This is a gallery, and now assume that for n we have a chamber complex. And now we have two chambers in Sm1, W1 star, which is W11 inside W12, etc. And I. Is 1, 2. And we have to build a gallery between them. So denoted by Wn-1 E, the intersection of Wn1 and Wn2. So this is the dimension n-1 unless they are equal, in which case we can assume with paragraphs of the generality that they are not equal.
I think you should either switch to Sn+1.
Yes, we are in n+1. Huh?
Yes.
And now, let W3 star n-1 be chamber in SNQ. Any chamber that coordinate is this. And now, identify W1n with FQN. And using this identification, we can think of, if we shorten this one by 1, it will be a chamber in SNQ. Let's denote by W1 star theta. This is W11, W1, and -1. This is chamber SNQ. So now we have a gallery from this one to this one.
I'm confused. You had a sequential complex. All your spaces were in FQ to n+1.
Yes.
So the complex was Sn plus 1.
So we take a chamber in Sn plus 1.
So what you wrote is just N.
This is the injection assumption.
That's an
Ah,
injection.
okay,
So now we take two chambers in the next level. And if we shorten it by 1, we get a chamber in the previous one. And we have to use an edification of the last one with FQN. So now, by the induction assumption, we have a gallery, let's call it C0 with CR in S and Q, with C0 W1 star tilde and CR is W2. And now we just do the same with the other chamber. We identify W2N FQN, and now you can take any identification. We have to be compatible with the previous one in a certain way that both identifications agree on the intersection W1N intersection W2N, which should be possible. And we have the gallery in S and Q, C tag 0 to C tag S, when C tag 0 is W3, and C tag S is W2 tilde, the short. And now we build the gallery between the original chambers. The gallery in S and plus 1Q. Take the first gallery. And add to each one the W and 1. And then we take the second gallery and add to it W2N. And this is just W2. This is W1. And the intersection between two chambers here is a wall because they are different exactly by one coordinate. And the intersection here is CR and C0, which are the same one. So with this, we see that if the maximal length of a gallery here is some k, then here it will be 2k, so we get 2 minus 1. But we can do better, much better than that. We can take, instead of taking W3 to be any arbitrary chamber. If this one, we can take a chamber that is as close as we can to W1, and then it will be much shorter.
That what?
We can take a specific W3, and actually you can take the first gallery to be of length n minus 1. Just take the intersection. W3 n minus 1 is Wn
Yeah.
intersection Wn1 intersection Wn2.
Instead of choosing it completely arbitrary,
Yeah.
you will choose it in what
So
way?
W3 n minus 2 will be W n minus 1 3 intersection with W1 n minus 1, and so on. And then this gallery will be of length exactly n minus 1. So we get that if Dn is the diameter of S and Q, then for S n plus 1Q, we have n minus 1 for the first gallery, n for the first gallery, plus Dn. That. So
This
that's
is-
order times square.
Instead of n square or even n square over 2 or something. Okay. You sent me another proof, right? It's another or it's very similar to one of them?
But I didn't finish.
Oh, I see, I didn't read them, I just thought, okay. Okay, good. Okay, we stop here and next time I will do the